friends, good morning. So today we are going to discuss about the SSB demodulation techniques. So last class we discussed about the SSB modulation techniques, single sideband modulation techniques. Today we can discuss SSB demodulation techniques. So before going to the demodulation, so what is a modulated wave? So what is the equation for the modulated wave, that is SSB, single sideband modulated wave? So how it will be generated? So what is the final equation? So based on the final equation, you can receive the same equation at the received side for demodulation. So overall, demodulation is getting the original signal. So what is the modulating signal m of t, which is transmitted at the transmit side, can be retrieved, say, at the receiver side by the operation called demodulation. So here you can see the SSB modulation method. It is a single sideband. We are transmitting, we are forwarding only one sideband. It may be upper sideband or lower sideband. So here you can see the two sidebands. It is the lower sideband. This one is the upper sideband. So based on that, our requirement or application, you can transmit the any one of the sideband. It may be upper sideband or lower sideband. So this is the input signal, modulating signal m of t equal to am into cos of fmt. Then another input signal is carrier signal. So it is c of t equal to ac into cos of fct, where ac is the amplitude of the modulating carrier signal and fc is the carrier frequency. Similarly, for the m of t equal to am into cos of fmt, where am indicates it is the magnitude or amplitude of the modulating signal and fm is the frequency of the modulating signal. So after the modulation, mathematically, the upper sideband wave or single sideband, that is upper sideband of the SSB modulated wave, S of t is equal to am ac by 2 cos 2 pi fc plus fm into t, because it is about the carrier frequency, that is fc plus fm, it is upper sideband. Whereas coming to the other one is lower sideband, which is given by S of t, am ac by 2 cos 2 pi fc minus fm into t. So it is lower sideband. So below to the carrier frequency, that is minus fc minus fm. So it is lower sideband. So you can have the both upper sideband as well as the lower sideband. Based on their requirement, we can have the modulation. Suppose you want to transmit the upper sideband, you can use the above equation, S of t equal to am ac by 2 cos 2 pi fc plus fm into t. And similarly, if you want to transmit the lower sideband, you have to take the modulated wave S of t equal to am ac by 2 cos 2 pi fc minus fm t. So that is the fc minus fm lower sideband. So you can transmit the any one of the sidebands. Then coming to the actual topic today's, that is one of the demodulation techniques for the SSB. So once you have the transmission is over, that is modulation, SSB modulation is over, the modulated wave S of t, which you have seen, it may be upper sideband and lower sideband. It is upper sideband, it is a lower sideband. So you can receive the any one of the sideband. So that is depends upon the application or requirement. If you want to transmit the upper sideband, you can receive the upper sideband wave, that is S of t here. If you want to transmit the lower sideband, you can receive the lower sideband at the input of the coherent detector. So coherent detector or detection for the SSB modulated wave. So already you know that what is the coherence. So that is the frequency or phase in phase of the frequency. So which is the frequency used at the carrier side, that means transmit side. So locally we are using the local oscillator here, that is the local oscillator which can generate the carrier frequency AC cos 2 pi fc. There here we are going to have the frequency as fc. Same coming to the transmit side, there is a modulator. There also we are going to use the two inputs, one from the input signal, that is modulating signal m of t. Another signal is by the arrangement of the local oscillator, we can generate the carrier frequency c of t. So the carrier frequency at the transmit side, what we have generated, will be same as the carrier frequency fc is generated by the local oscillator in case of the coherent detector also. So both are in phase or in frequency, so that this is called coherent detector. Coherency. The carrier frequency at transmitter is equal to the carrier frequency at the receiver side, so that both are same, in sync, in synchronization. So that is this demodulation technique is called coherent detector or coherent detection. So you can see here the components: product modulator, local oscillator, and low pass filter. So along with these three components, there is a received input, which is the modulated wave S of t. So S of t may be, so that means SSBSC means single sideband suppressor carrier. For both case, you take the A modulation, we are transmitting the carrier signal under two sidebands. Whereas coming to the DSBSC wave, double sideband suppressor carrier, we are transmitting only two sidebands and suppressing the carrier also. So that is DSBSC wave. Whereas coming to the SSB, here we are transmitting only one sideband and suppressing the carrier signal and one sideband. Along with the carrier signal, we are suppressing the one sideband also, so that it is a single sideband suppressor carrier. So received signal is, it may be upper sideband or lower sideband. So depends upon our transmission. So once you have the input signal, received signal S of t, and you have to arrange the local oscillator here, which can generate the carrier signal C of t equal to AC cos 2 pi ft. So both input signals, received modulated wave, SSB modulated wave S of t, and carrier signal from the local oscillator is given to the product modulator. So what is the product modulator? Which can generate the product of given input signals. So what are the given input signals here? The one is the received signal, that is modulated wave SSB. Another is carrier signal from the local oscillator. So both input signals are given to the product modulator, which can generate the product of these input signal, which is indicated by V of t. So V of t is the output of the product modulator, which can generated with the inputs of S of t, that is the SSB upper sideband modulated wave. Another one is the local oscillator frequency signal, carrier signal C of t. So that means you can say that V of t equal to input signal S of t into locally generated carrier signal C of t. So that is V of t, S of t into C of t signal. So that we are getting the V of t signal. It is a product of the received modulated wave S of t and locally generated carrier signal C of t. So once you have this V of t signal, this is a combination of the high frequency component and low frequency. So our aim is detection of the modulating signal. So we have to detect or retrieve or recover the original modulating signal M of t from the modulated wave with the support of locally generated carrier frequency. So because we are suppressing the carrier at the transmit side, for retrieving purpose, you have to arrange the local oscillator, which can generate the carrier signal, which is similar to our carrier signal at transmit side. So that V of t is a combination of the high frequency as well as the low frequency. So with the support of the low pass filter, we can reject the high frequency components and allows the only low frequency components, because it is a low pass filter which can allows the only low frequency components and rejects the high frequency components. So once you have the operation of the low pass filter which can allows the only low frequency components, rejects the high frequency components, then finally we are going to get this our demodulated wave output, that is M of t here. We are going to get our original signal M of t. So that is the basic diagram operations. Receiving the input signal S of t, and by the arrangement of the local oscillator, we can generate the local carrier signal C of t. So by the operation of the product, we can generate the product of these two input signals, that is indicated by V of t. So V of t is a combination of the high frequency as well as the low frequency components, so that we can reject we can eliminate we can filter the high frequency components by the arrangement of the low pass filter and allows the only low frequency components that is given by the similar to our original modulating signal M of t. Finally, the output of the low pass filter which can generate or produce our original modulating signal M of t only. This is a black diagram representation. Coming to the mathematical equations, so you know that there are two sidebands. SSB consists of the two sidebands, upper sideband as well as the lower sideband. So the upper one is indicates the lower sideband because carrier frequency minus FM will get the below to the carrier frequency, so it is lower sideband. For this case, we are going to consider the carrier signal C of t equal to AC cos 2 pi fct. For a received input signal, S of t is lower sideband, so that AM AC by cos 2 pi fc minus fm into t. Another signal is local oscillator generates the carrier signal which is given by C of t equal to AC cos 2 pi fct. So once you have these two, so the output of the product modulator is given by E of t. E of t nothing but product of both input signals C of t and S of t. So by the application of this cos A cos B formula, by substituting what is S of t, what is the C of t. What is S of t? It is a lower sideband. AM AC by 2 cos 2 pi fc minus fm into t into carrier signal AC of t, AC cos 2 pi fct. So by the combination of these two, you can have the combination of both low frequency and high frequency components. By the Fourier transform, we will get the expression cos A cos B formula. So by application of this one, you can have these expansions. So from this, you can separate the low frequency as well as the high frequency components. So take the AM AC square by 4 cos 2 pi fmt. It is a modulating signal low frequency. So whereas coming to the AC square AM by 4 cos 2 pi 2 fc minus fmt into t. 2 fc is the high frequency. Already the carrier frequency is the high frequency components. So here we are getting the 2 times to the carrier frequency 2 fc. So it is the entire term is a high frequency component. This high frequency term can be filtered or rejected by the arrangement of the low pass filter, which is last element of the diagram. You can see the diagram. So it is a low pass filter is last element which can rejects the high frequency and allows the only low frequency component. So this high frequency term can be filtered by the low pass filter and allows the only low frequency FM 2 pi FM is FM is our modulating signal frequency, which is low frequency audio frequency range. So it can be allowed. So that indicates the generation of our original modulating signal by the coherent detector. So similarly, you can take this V0 AM AC square by 4 cos 2 pi fmt is the original or modulating signal after the demodulation. So suppose we take we are going to consider the low pass filter, that is the lower sideband. So suppose you want to consider the upper sideband. So that is S of t equal to AM AC by 2 cos 2 pi fc plus fm. It is a upper sideband. So previous case we have considered the received input signal S of t modulated wave is a lower sideband. For this case, we are going to take the operation of the detection. Finally, we are going to retrieve the original signal M of t equal to AM AC by 2 cos 2 pi fmt, our original modulating signal. This is how we are going to recover retrieve the original signal by the consideration of the lower sideband. For this case, the second case, you have to use the received input signal S of t is the upper sideband AM AC by 2 cos 2 pi fc plus fm into t. So similarly, you have to get the carrier signal from the locally arranged local oscillator C of t equal to AC cos 2 pi fct. So after the product modulator, we are going to have the output V of t equal to product of the received input signal S of t and carrier signal C of t. So by substituting these two, we will get the V of t equal to AM AC by 2 cos 2 pi fc plus fm into t into carrier signal. This is the carrier signal. This is the upper sideband. So by the formula of the cos A plus cos B, the expansion will get the combination of both the upper sideband higher frequency component as well as the lower frequency components. So by this finally this equation gives the AM AC square by 4 cos 2 pi FMT. It is a low frequency component, and whereas coming to this one, it is a high frequency component. So 2 FC plus FM. So we are getting here 2 times the highest frequency components. So that is the component is a high frequency component. So our aim is always our modulating signal lies in the audio frequency range, low frequency range, 20 Hz to 20 kHz only. So that by the arrangement of the low pass filter, we can reject this high frequency components. So this can be filtered and allows the only low frequency AM AC square by 4 cos 2 pi FMT. So this is our wanted final signal. So that is V naught of T. After filtering operation, we are getting the V naught of T, AM AC square by 4 cos 2 pi FMT. Here we have to take the scaling factor of AC square by 4 is some scaling factor. So it can be given to the original, improve the or reduce the signal strength or amplitude of the modulating signal. AM AC square 4. So actually the signal M of T equal to AM into cos 2 pi FMT. So because of this, AC square by 4 can be act as a scaling factor. So previous case also for the consideration of low pass filter, lower sideband. So there is also you are going to have the scaling factor of AC square by 4 only. So finally our aim is by the operation of the coherent detection or coherent detector, you can retrieve the original signal V naught of T. So this is about the coherent detection of the SSB demodulation. So overall, you can see all the AM modulation techniques from the beginning. AM modulated wave is consist of this signal, both carrier signal as well as the two sidebands. There is transmission. So whereas coming to retrieving, so there is a process of filtering rejecting the carrier frequency as well as the high frequency components. So I'm getting the only low frequency components which is equal to M of T, which is given by AM into cos 2 pi FMT only. So you take any case, so demodulation of the AM modulated wave or demodulation of the DSBC wave or demodulation of the SSB, for both three cases, finally we have to retrieve the original signal of M of T only. So M of T is our modulating signal, which is basically consists of the information which can be transmitted at the transmitter side. So whereas coming to the receiver side, so after the modulation operation at transmit side, it is a combination of the carrier signal as well as the modulating signal. Both combined together take the operation of the modulation. So modulation here, the conversion of the low frequency component into high frequency. So because it is a combination of the modulating signal frequency FM and carrier frequency FC, both will be transmitted in high frequency range. Coming to the receiver side, demodulation operation takes place. So by the demodulation, you can filter the high frequency component and allows the only low frequency components only. So this is you can observe all the demodulation techniques. Finally, our aim is you have to retrieve the M of T signal only. What is M of T? Is equal to AM into cos 2 pi FMT. So FMT is our modulating signal frequency. So modulating signal frequency always lie in a audio frequency range, that is 20 Hz to 20 kHz only. So this is you can observe all the demodulation techniques from the AM modulation, DSBC wave and SSB. So with this we have completed the demodulation techniques of the SSB also. So both cases, the coherent indication, demodulation of the SSB modulated wave. So that means coherence indication in synchronization of the frequency. So frequency used for the transmission or modulation at the transmit side is carrier frequency FC. The same frequency can be generated at the received side, that is the demodulation operation side, by the arrangement of the local oscillator which can generate the carrier frequency C of t equal to AC into cos 2 pi fct, where fc is the carrier frequency of the locally arranged local oscillator, so which is similar to our carrier frequency of the transmitter fc. Both are in synchronization, so that this detection is called a coherent detection. So with this we have completed the demodulation also. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.